Hi, good morning. Today we are going to look at global counter encryption problem. So assume that we use a counter mode encryption using 4-bit global counter. The counter value is currently 0001. For the global counter value or the global counter scheme, the seed is formed directly from the global counter value. Okay. Assume that the counter is incremented before being used for encryption. So that's the same with in class. Use the following block cipher encryption. So you're given the following input and output of the block cipher. And then next, the problem states that you have block A with value 1110 located at address 1000, which is dirty and needs to be written back. Okay, so here we have block A with a value of 1110 at address 1000. And then block B with value 1110 also located at the address 1001. It's also dirty and needs to be written back. And the question then asks, for each of the block, calculate the encryption seed that is used for encryption pad, and the ciphertext. Now let's review this encryption scheme a little bit. So with this global counter encryption scheme, you start with a seed, and then the seed in this case will be the counter value after it's incremented. And then this seed is encrypted to produce a pad. Then the pad is XOR with the content or the value of a block. And after it's XOR, we obtain the ciphertext, which then can be written to memory, right? So after we encrypt it, we can write it to memory. All right, so let's get started. First of all, here we will have a counter global counter. The current value is 0001. Okay, let's start with block A. So block A needs to be written back, and here, in order to do that, we have to obtain its seed. In this case, the seed is the counter value incremented by 1. Okay, so this will be 0010. Okay, and then the pad is then the encrypted version of 0010. And if we look at here, this is where it is, right? The input of the block cipher 0010, the output is 1100. All right, so next we have 1, let me see what it is, 1100. All right, next, so the ciphertext is basically pad XOR with value of block A, which is then okay, so the pad 1100 XOR with the value 1110. This leads to 0. So 1 XOR 1 is 0. 1 XOR 1 is 0. 0 XOR 1 is 1. 0 XOR 0 is 0. Okay. So then this is the value of block A that will be written back to memory. Now let's look at block B. So the seed is basically global counter incremented by 1. Now the value of the global counter is no longer 001 because we already incremented when we use it for seed of block A. Therefore, the seed is the incremented version of 0010, which means this is 0011. And then the pad is therefore for block B 00, so it will be the encrypted of 0011. So 0011 right here. So the encrypted version is 1011. Okay. And therefore the ciphertext for block B will be the pad and value of block B, which is 1011 XOR with value of B, which is 1110. This leads to 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0, 1 XOR 0 is 1. So therefore, you can notice here that initially block A and block B did have the same values in plain text. Now, because of the counter mode encryption, there is ciphertext diversity, meaning that when they are written to memory, ciphertext of block A and ciphertext of block B are different, right? So they don't, they are not easily subject to frequency analysis, because even when the plain text is the same, but the seed that is used is different, and therefore the ciphertext values are different. Okay, so notice also incrementing the counter value ensures that the seed doesn't get reused, and therefore we remove the vulnerability of counter mode encryption, right? So we cannot allow seeds to be reused. All right.